So let's get started. So my name is Xianyuan Zhang from Institute of AI Industry Research, short for AIR, Tsinghua University. And in this lecture, so I will talk about the data-driven methods for intelligent urban transportation systems. It seems I started already. Okay. Okay, let's begin. Okay, so this lecture will talk about how do we design data-driven methods to solve some of the urban transportation problems. Especially we are looking at how to use some of the data engineering and AI method and to address some of the commonly available urban transportation problems. And what are the design philosophies behind these systems? And what are the future perspectives? And so this is the, not working? Okay, so this is the agenda for this lecture. So I will first describe some of the emerging data sources for urban transportation problems, and especially what are the characteristics of the spatial temporal data, and what are the modeling challenges. And the second, I will introduce a series of data-driven transportation applications. Specifically, there is one example for how do we monitoring traffic states, how do we reliable forecast the traffic conditions in the future, and how do we perform data-driven planning. And the last one is a little example on how do we use data-driven methods for operation management. And I also talk about some of the future perspectives and how do we use this kind of data-driven method to solve some of the future problems. And so let's first talk about the data. So because it's the lecture is about data-driven method, so data is everything. And that's at about 2 decades ago. So in these 2 decades, so because of the development of ubiquitous computing and some of the mobile technologies, we have massive amount of self-generated data that are generating every day in the urban space. And to give give you some numbers, and for example, in the urban sensor networks, a typical example is a license plate recognition camera on the intersections. Even for a small city in China, so there could be as many as 40,000 vehicle records that passing the intersection in a day. And back in 2013, and if you look at the New York City, and you will get about 500,000 taxi trip trajectories in a single day. And right now we have more of the e-hailing services like the Uber and Didi. And we now even have more taxi trajectories generated every day. And another big data source is the mobile phone data. And for example, in Suzhou, in the city of Suzhou, in just one day, there could be as many as 200 million mobile phone records that are generated one day. So that occupies a space that about 23 gigabytes. And there is also a lot of other data sources that can be used to solve transportation problems. For example, the smart car data for buses and for subways. And also, right now we have the ride sharing services, and we also have a lot of bike trajectories. This can also be used to solve some other interesting problems. And I think another very potential and important future data sources is the sensory data from the autonomous vehicle. And this can be a game changer to change a lot of things for future intelligent transportation systems. And so let's look at a short video. So this video basically shows the trajectories from the taxis, buses, and trucks. How do I get rid of this one? This basically shows the variation of trajectories from taxis, the trucks, and the buses over the single day in Shenzhen. You can see the very dynamic pattern that evolves over a day, and from morning to evening, that captures the rhythm of the city. And also you can see there is actually a massive amount of vehicles and also the highly complex dynamics that keep changing in a single day. So this contains a lot of information. And for the first time in the history, basically, we do not need to rely on building analytical models based on assumptions, but rather we're directly using this data. We can directly observe how the system actually works and what are the dynamics inside the system. So that actually changes a lot of things. So basically, if you there is a lot of modern transportation applications that are already powered by the big data, and in other words, they are already data-driven. And one of the most commonly used services are the online digital maps. For example, the Google Maps, the Baidu Maps, and the Gaode Maps. So usually, currently nowadays, all these services, they have some kind of data-driven traffic state estimation or traffic state forecasting algorithms running behind. They keep collecting the trajectory information from the user's devices and use those fresh information to update their traffic state information. And they can use this information to provide routing and navigation and then a lot of other provide a lot of other travel information to the users. And about 2 decades ago, so most of the transportation planning is not data-driven. So the traditional way to do that is to find a lot of people and conduct a transportation survey. Basically, we ask a lot of people to fill a lot of questionnaires. They ask questions like, where do you live and where do you work and how long do you commute for work and which mode of transportation you use to do this commuting. And but right now, so we do not need to rely on this kind of surveys. We directly use the data we have to see what exactly are the traffic flows coming from one place to another place in the city. So actually, this is a much more accurate and it can make more reliable future planning for our systems. And since we get this amount of data, so basically we get a good understanding about the current condition of the entire system. So in that case, we can do better traffic management and control, and we can do better congestion relief, and we can also detect the accident in the road network early, and conduct early intervention. And if we know the road speed and the volume, traffic volume on this road for every link in the network, we can also compute the vehicle emissions, the network-wide vehicle emissions. And this can also be used to help us to improve some of the infrastructures to get a greener city. And recently there is also a lot of studies that trying to borrow data-driven methods to solve the signal timing optimization problems. Although this problem right now is not fully data-driven, but there is some very good progress. They trying to use data-driven methods to estimate the volume traffic demand on the intersection and use some of the transportation engineering tools to optimize the signal control to minimize the signal intersection delay. So basically, we already have this kind of data-driven applications. And there is also a clear shift from the previously engineering-based method to the data-driven based method. And the thing or the data behind this kind of applications is what we call the spatial temporal data. We call it spatial temporal data because the data contains both the spatial property and the temporal property. And we can basically classify all this kind of spatial temporal data in the city into 6 categories. Depending on the data structure, whether it's a point-based or network-based, and we can classify them into these kind of categories. And the most simple type of the data is actually the POI, is the spatial temporal static data. So everything is static. A typical example for this is the point of interest data on our online digital maps. So point of interest data means the venue labels on your online digital maps to suggesting whether this is a restaurant, whether it's a hospital, whether it's a school. So it's just purely static data. And we have a lot of fixed sensors in the road in the city. For example, the license plate recognition cameras. So these are the spatial static and temporal dynamics data. So the location is fixed, but it keeps generating time series readings. and it provides some of useful temporal information. And another more complex data is the spatial and temporal dynamic point data. So a typical example for this kind of data is the social media checking data. For example, when you're checking on Weibo, the Foursquare and Twitter, so basically you will generate tweets with a geolocation attached. So these are typical examples of the spatial temporal dynamic point data. And if we look at a more complex type of data, the network-based data. So the simplest one is the spatial temporal static network data is the road and the transportation network data. So data contains somewhat complex topologies. And if we overlay the traffic states onto the road network and we inject the time evolving the traffic states, then it becomes the spatial static and the temporal dynamic network-based data. And the last one is, and also the most informative but more complex one is the trajectories. So these are the spatial temporal dynamic network data. It's a series of ordered points and with both timestamps and also the geolocations. So these are the most commonly used data that we usually use for data-driven transportation modeling. And so this kind of the spatial temporal data has some unique characteristics. It is different from the image data, text data, and all the other data that we typically encounter in the field of data science or AI. So basically because it encodes both spatial and temporal information, so it has some spatial properties and also the temporal properties. For the spatial property, I think the most important property is the distance, the notion of distance. So the 2 points, if they are close to each other, then the functions behind these 2 points are most likely very similar. So that is the first law of the geography. And for example, the two adjacent road segments may possess similar traffic state conditions. And also we have the triangle inequality. So this has very important usage in the applications like routing and in other things. And also we need to consider hierarchy. And because if you aggregate your spatial temporal data to different granularity, you might get very different results. For example, if you aggregate into the district level, or you aggregate to the zip code level, or the road segment level, and if you run the same analysis, it is likely you get very different results. So basically, granularity is very important if you want to design a suitable application using this kind of data. And also we have the city structures behind. So because in the city, we have the road network, and also we have the functional regions in the city. So these also have important impact on the patterns that you observe in the data. And also it's like, we also have the temporal properties. And basically it's the temporal closeness, which is similar to spatial closeness. The 2 timestamp is close, then most likely the functional behind this is very similar. And also we have the periodicity. For example, in every day we have the morning peak, we have the evening peak, and at night